Hello, so in this video we will be talking about electron affinity, and similar to the ionization energy movie, video, whatever you want to call it, we'll start by talking through the definition and then walk through the periodic trend and then end with a problem where we try to explain what's going on with nitrogen, which the electron affinity of nitrogen violates the periodic trend for electron affinity. So first, just to start with the definition, so electron affinity is a measure of how much an atom, and I'll kind of underline, it's a measure of how much an atom sort of is happy to accept an electron. And so the formal definition is that if we have an atom, a neutral atom, with equal numbers of protons and electrons kind of hanging out, and we send a free electron its way, that free electron, right, is a naked negative charge kind of hanging out. It is looking for, say, a nucleus to associate with so that it can have some positive to balance it out. And so when that electron and that atom find one another, they combine to form an anion, an atom with a minus charge, and they release energy. And this energy released is the energy that we list as electron affinity. So it's that energy that's released. And I think a key kind of point here is that ionization energy, where we strip an electron away from an atom, that requires energy. We have to hit that atom with energy to get it to spit out an electron. With electron affinity, it's actually generally downhill, energetically downhill, or beneficial or favorable for an electron to associate with an atom in order to make an anion. And so we release energy, as we say here. All right, so the periodic trend for electron affinity is far weaker or less consistent than what you see for ionization energy, but there's a very rough trend as we go across the periodic table. And so I'll sort of show some data. I copied this table out of Chang. I did a better job this time of keeping things like the units and where the table is from. So this is table 8.3. So as we go across the periodic table, kind of if you look as we go across a row, generally the electron affinities get larger and larger as we move towards the right-hand side, although that is not true for the very end. That's not true for the noble gases. And that's something else that, yeah, that is something that we might try to explain as well, although I won't do that in this video. And so the general periodic trend for electron affinity is that as we move this way, electron affinity increases, which means that more energy is released when an electron comes along to make the anion, to make the negatively charged atom, which is another thing that it's more favorable to get atom minus. And so as a way to think about this, for example, F minus is much more favorable to form than lithium minus by addition of an electron. That's kind of what all of this means. The vertical trend is very weak. And so for all intents and purposes, we can say there's not really a strong vertical trend as we go up and down a column. But generally speaking, as we move across the periodic table, electron affinity becomes more favorable. Atoms on the right-hand side of the periodic table are happier to accept electrons than atoms on the left-hand side of the periodic table. As I already alluded to, this trend is not super strong, right? If you were to plot these numbers, you do not get a line with a really good R-squared sort of correlation, right? And so there's actually quite a few exceptions. In this video, I'm going to talk through this particular exception of nitrogen, right? So we would expect, just based on the trend, that nitrogen should have an electron affinity somewhere in between carbon and nitrogen. But it does not, right? The electron affinity is 0. It's extremely low, and this value means that N does not easily accept an electron to form N minus. That's what that means. And the question we want to answer is why. And so that's what I'll try to answer on the next slide here. And so when we're trying to think about why it may be unfavorable to add an electron to nitrogen, or at least why it's not particularly favorable to add an electron to nitrogen, we want to start the same way we would start an ionization energy problem, by drawing out the electron configuration of N. In general, with electron configurations, you can draw out the entire electron configuration of N. It's also reasonable to draw out just the electron configuration of the valence electrons, but I'll do the entire electron configuration because nitrogen only has 7 electrons total. It's in this 2p block. And so I know that I'm kind of going to deal with the 1s, the 2s, and the 2p's, and I'm going to fill in those 7 electrons. So 1s, 2s, and 3 2p orbitals at equal energy. And I'm going to fill in the 7 electrons. Now I'll make them blue. 1, 2, 3, 4, 5, 6, 7. Great. There's my 7 electrons. So the question is, why is it not favorable to add another? And I'm going to write another in red. And so the way I like to do this is to say, all right, if I were to add another electron, where would it go? And the answer in this case is that there's 3 equivalent answers. It doesn't matter which 2p orbital we put it in. I'll put it here in this middle one. It would go into one of the 2p orbitals. And when the electron enters that 2p orbital, it would find that it has a roommate. Another way of saying this is that that new electron would be paired. And that gets at one of the sort of fundamental interactions that we want to be really mindful of, which is that there is electron repulsion because of minus repulsion, because negatively charged things repel one another. And that electron repulsion creates an energy penalty when electrons are paired, right? And so that is the key. That's the key here, is just to recognize that adding that additional electron, that red electron, is actually pretty tough, or it's not particularly favorable, because that new electron would be paired, and there's a pairing energy penalty. And so I will leave it there.